Good afternoon, everyone. Today, I will make a presentation that is based on the homonymous paper titled Towards a Large-Scale Empirical Assessment of Web APIs Evolution that we will present in May 2021 in the ICWE conference. So we have to start from the definition of a Web API. Web application programming interfaces, also known as APIs, are used to remotely access software services over the HTTP and HTTPS protocols. They make it possible to build a complex application very quickly using third-party data sources and reusing software delivered as a services. Another advantage of using API is that you can reuse software written in different languages without the need to translate them in the language that you are currently using for your own project. But API systems many times evolve during their lifetime for different reasons. These changes could have a minor or a severe impact on clients, potentially breaking their functionalities. The impact of change depends on the type of the operation that the developers want to introduce in the system. For example, adding features usually doesn't produce any kind of impact on clients. But on the other hand, editing or removing implemented features could lead to break the expected client's behavior. To mitigate this, service owner, service provider can use different techniques to guarantee the stability of their offering, for example, reveal a preview of a new experimental versions only to selected clients, or they can choose to support one or more versions of an API at the same time, maybe introducing a deadline for the switch off of the older one, the original one. In our work, we focused on those API projects in which the web interfaces are described using OpenAPI specification language. The OpenAPI specification was originally based on the Swagger specification that was donated by the Smart Beer software company, and now are maintained by the OpenAPI initiative that as an open governance structure under the Linux Foundation is focused on creating, evolving, and promoting a vendor-neutral description format. So we developed a software, hereinafter I will call it a crawler, that is responsible to check for new OpenAPI specification files appearing on GitHub, download them, and keep updated their histories on our database. In December 2020, the crawler performed a complete GitHub scan, discovering more than 4,000 open source API descriptions in both Swagger and the new one, OpenAPI format. It discovered also more than 34,000 commits, which represent the project histories, and something less than 40% of them containing valid specification files. We discovered also that 55% of the collected APIs contain more than one commit. We retrieved also some metadata associated to each artifact, like, for example, the comment timestamp, the version identifier, and the API title. In this slide, we can observe how much the Swagger and OpenAPI standards become very popular over the last 7 years. Their presence on GitHub increased from 2015 to 2020 by 82 times. So it's widely used. Our goal is to assess the feasibility of using this collected API description in order to study how these web APIs evolve over time. We aim to answer the following research questions. Do the API artifacts have a sufficient long history? What kind of changes can be detected by analyzing basic metadata associated with this artifact? How stable are API artifacts over time? And the latter, do APIs tend to grow or shrink over time? In order to answer the previous questions, we must first define the metric chosen for our study. We choose as simple as a meaningful metric, which is the API size. It is basically the count of a published operation by each API. In the histogram, I reported the API size distribution for every commit. As you can see, a few hundred commits don't contain any operation, and also the size metric follows an exponential distribution with a tail that reaches up to 357 operations. Here you can see a very simple example that is useful to understand the size metric. In the left, there is a simple OpenAPI specification file in which you can observe two path entries, init and handle. Handle path, it's reachable using 3 different HTTP verbs that are into specific get, post, and delete. Using the previous definition, here we can count 4 different operations described. So our size is exactly 4. For showing this example, I used the OpenAPI to3, that is a tool developed by our colleague Suela Serbo, that is available at this web address. This tool is particularly interesting, especially if you need to visualize an API description and you need some dynamic interaction with it. So if you are curious, I suggest you to take a look. Despite the large number of APIs collected in the next slide, I want to show you a set of few API cases with different evolution histories. The first one is Docstore API. This particular example has a commit where 192 operations were deleted at once. Here you can see. Then it started slowly growing during the next 254 days, adding 85 operations more. As you can see, on the day 394, there was a commit that inserted 122 operations to the API. And after that, we can observe minimal variation in its size, with a variation of 5 operations from day 394 to 574. While during the first half of his history, there are no changes in version metadata, after the date 279, the developer starts to change version more frequently. This could be a perfect example of a breaking change here, a breaking change introduction, probably, we don't know, caused by a code refactoring activity. The next one is the Kubermatic example. In Kubermatic example, we can observe an API which both grows and shrinks over its history of almost 200 commits over more than 2 years, eventually more than tripling its initial size. It grows rapidly with an average speed of 1.77 operations per day. So I don't have the time to go over the history of all the other 873 APIs we have collected. So let's look at all of them together. In this figure, we can see the entire history of all the APIs we have collected, which have more than 10 commits. Each dot represents a commit. Its horizontal position shows which API changed, while the vertical position represents when the change occurred, relative to the time of the initial commit for the corresponding API. The colors highlight how many commits have been found for each API. we can see that for some APIs, there are commits spanning across more than 4 years, and that there are 280 APIs, which, as we said before, have more than 10 commits. We define also the age of the API as the time interval between the last commit and the first commit on its history. In the figure, we can observe the age distribution of the APIs in our collection. Most APIs have an age of 0 here. This indicates that those APIs have only one commit in their history. On the other hand, there are also some APIs whose history span up to 5 years, which make them potential subjects for further study. We noted also that in many APIs, the specification files are pushed only once, and after that, they are no longer touched. Is it clear that the number of versions is bound by the number of commits, since every observable change of the version identifier requires a new commit to store the updated API specification, but commits do not always match version increments. Different API developers follow different version practice, ranging from version identifiers incremented every other commit to API histories with only a few explicitly identified versions over hundreds of commits. We also found examples in which the title of the API itself will change, while the specification document used to describe it would remain the same. How likely is an API to change? To find out, for every commit, we plotted the age of the API on the x-axis against the time since the previous commit on the y-axis. We can see that the interval between commits remains stable as the age of the API increases. We classify APIs in terms of whether they grow, shrink, or simply do not change, we obtain the groups shown in these two tables. In the left, in the first tables, are counted the APIs that have grown larger or smaller over the entire history. Here, we can see that 6% of them shrink, 45% remain stable, and 50% of the APIs grow. If we also consider changes occurring at every commit, as shown in the table on the right, we can see that 42% of the APIs keep a constant size in all of their commits. Moreover, there are only 17 APIs in which changes are detected in their intermediate size, but end up with the same size as the initial one. Furthermore, we have 16% of the APIs have a history with some commits increasing their size, while others are reducing them. In summary, do the API artifacts have a sufficient long history? Yes, thanks to the growing adoption of the OpenAPI specification language, a sample of 875 APIs with a history of more than 2 commits can be found on GitHub. And also, we found many more API description artifacts, more than 1,300 to be precise, without a commit history of significant length. While these are still interesting to analyze, it remains to be seen whether developers pushed only a single commit because their APIs were committed only when stable, or we have crawled the repositories of projects which never went beyond the first commit. What kind of change can be detected by analyzing the basic metadata associated with the artifacts? And here the reply is simple. It's commits do not always match version increments as we've seen before. How stable are API artifacts over time? The likelihood of a change does not depend on the age. Okay. Regarding the API evolution counted, we have focused on one possible API size metric, which has allowed us to detect changes for more than half of the APIs collected. For sure, we will need a more in-depth analysis of API artifacts to detect and measure changes beyond their size, as for example, to spot the changes in parameters, responses, and schema definitions. By only looking at the size, we could show that the majority of the APIs in our sample, which change their size, have a tendency to grow larger over time. And there is one more thing. Another example is a interesting example is Voyager. Voyager is an API example which has 40 commits, in which 16 different versions are distributed. However, we can notice that its size remained the same during its whole evolution time. This case is an example where a more detailed metric is required to detect changes. So the size is not sufficient to describe the history of this example. In fact, we observed that 23 commits of its history contain schema definition changes, 6 contain changes to path parameter definition, and 2 are related to response modification. Furthermore, in its history, developers push 6 major and 8 minor version upgrades, always without changing the operations number. This means that our work is not finished. So, as future work, we plan to we need to investigate more on how these artifacts can be used to trace, measure, and classify changes on API structure during their lifetime. Also, we have to define heuristics. We want to define heuristics for classifying the changes using more metrics like HTTP methods, paths, and query parameters and properties of response objects. We also plan to establish a nonlinear partial order relationship within the artifacts, which may undergo forks and merges across different repositories. And well, we are open to your suggestion if you have some. Thank you for your attention. That's it.